Let's take a look at how the derivative of the temperature compares between the finite element solution and the exact solution. And the derivative of the temperature is important because it's related to the heat flux. This plot shows the comparison. On the vertical axis, I have the derivative of the temperature. On the horizontal axis, I have the distance along the bar. And the solid line is a finite element solution. The dashed line, as before, is the exact solution. So the exact solution is linear and decreasing, whereas the finite element solution is piecewise constant. And if I put up the graphic of the node sketched in, onto the to a figure of the bar, I see that over each element the derivative is constant, and that's because we assume that there's a linear variation of the temperature over each element. And it turns out that the error in the derivative is greater than the error in the temperature itself. To see that, if I say I want to look at the error at a location like that, the finite element solution says that the dt dx is that value here, okay, the corresponding value here, whereas the exact solution says it's that value, and that difference is an error. And then at the nodes, the derivative is discontinuous, which is a problem, but we can live with that problem. And from this, we can deduce that energy is not conserved for each element. And that's an important point. And to see that, let's take a look at a couple of elements. So let's say this is element 1, this is element 2, and if I draw a two-dimensional view of element 2, okay, and so I'm not showing the dimension perpendicular to the screen. And here the temperature, the way I picked the boundary conditions, the temperatures are increasing this way, so the heat is flowing this way from hot to cold. So the heat is coming in here, and I'll say that's the Q2 in, that's the heat flux coming into element 2, and if I multiply that by the area, I'll get the heat flow through there. And correspondingly, this would be the heat flow going out, and if I multiply that by the area, I will get the heat flow going out. So that's the heat flux, and multiplied by the area is the heat flow. And then I also have the heat being generated in that element. That's Q times the volume, area times delta X. If energy were conserved, the heat flow going in plus the heat generated would be equal to the heat going out. But this is saying that the heat flow going in, or the heat flux going in, is equal to the heat flow going out, which means that this is equal to this, and it's not accounting for the heat being generated in the element. So what happens to this heat being generated in the element? It turns out it goes into the adjacent element. So if I draw a corresponding graphic of element 1, okay, pardon my chicken scratch, and I say the heat going in is Q1 in times the area. Now there's a jump there, which means that this is greater than that, which is non-physical, right? Because these are adjacent, so this has to be equal to that according to physical reasoning, but it's not so in a finite element solution. And you can show that that difference is exactly equal to the heat being generated in the element. So it's taking the heat being generated in the element and adding it to the heat going in through the face of the adjoining element. That's non-physical, which means that energy is not conserved for each element. It's also not conserved for each infinitesimal element, because if that were the case, the differential equation would be satisfied exactly, and we saw that our finite element shape satisfies the differential equation poorly. But it turns out that the heat is, or energy is conserved in aggregate. We'll take a look at that next.